Shoot. I do. It's fascinating. Okay? Not going to go on a tangent. I'm not going to do it. All right? Again, if we're looking at stresses, right? We know normal stress is just force over area. Well, we need to know what force is acting. Well, we know that forces, say, now we have the z-axis. The forces in the z direction have to equal 0. So the force that's applied, based on our pressure in this cross-section, has to be equal to the force that's applied due to the resistance of our steel tank, right? Which is the Hooke stress, we are going to call it, times the area. And so the force that we're acting, right, the F over A again, which is essentially PZ over A. Well, PZ is just pressure times area. So pressure here being the internal pressure, the area over which this acts, well, it's going to be 2 times the radius, that's the height. And then the distance at which that we look at along the length of this cylinder is our delta x. So stress times area, PZ, pressure, area, that is the area that our Hooke stress is acting on. Well, 2 times the thickness, right? We're cutting through 2 times the cylinder thickness. Now what do we got for noise? Like the projectors? Oh, it's that? Electrical panel, great.
Yeah.
Nice. Yeah. Good thing you're a buffer. Okay. So we've got the force exerted by the pressure, right, which is stress times area, stress being the air pressure, area being 2R times delta x. The area over which the Hooke stress is acting, right? 2 times the thickness times the length over which we're looking at, which is delta x. So the delta x is canceled, and we end up simplifying this as PR over T, which equals PD over 2T. Why did I do that? Can't spell. We essentially have twice the stress that we saw in our sphere. Right? And as I mentioned on Monday, sphere is a very efficient means of having a pressure vessel. Right? We get essentially half the potential stress in our cross-section because we don't have these Hooke stresses that we have to account for. Again, as we did with our sphere, right, we wanted to look at the inner surface and the outer surface because our stress state changes. Right? We have these stress cubes that we could develop based on what's the stress on the inside surface and outer surface of our cylindrical vessel. If we do that again, we have essentially the same thing going on as we did with the sphere, except for now we've got a longitudinal stress in one direction, a Hooke stress in the other direction, and then radially, right, acting in and out of the tank, we're either going to see a pressure acting on the surface of our cube, that's if we're on the inner surface, or we're not going to see it at all, right? It's going to be 0 if we're on the outer surface of, say, a propane tank. There's no pressure there. Nice. Whatever you do, just keep it up. Or whatever you did, sorry. Right? As we know from going through a lot of the stress transformation parts of this class, as well as the last spherical problem, right? A change in stress, right, means that we're going to have some sort of shear stress. And so if we take and now look at our stress states for both the inner surface and the outer surface. Okay, so we have the outer surface, we have the inner surface. If we look at first our inner surface, We know with Mohr Circle, we're always plotting a single stress state, right? Each one of these black points on our x-axis are a point that corresponds to a stress block, right? Our little square. So if we look at, let's try and color code this, right? If we look at our green, see if I can zoom this in, right? If we look at our green Mohr Circle, right? When we plot a Mohr Circle, we plot 2 points. Okay? We know that those stress states that we had didn't have shear stress in them. But as we know from stress transformations, we might have shear stress if we start to rotate that element and look at a surface that's at an incline. And so if we look first at this green circle, right, the 2 points that we have our longitudinal stress and our Hooke stress. So this would essentially be sigma Hooke and sigma longitudinal, right? So what did we do to plot those points and to get that square? Well, up here, we essentially cut this cube, right, to look at a flat surface that's cut along the plane that includes our Hooke stress and our longitudinal stress. And we're going to do that same thing Right, so we're going to cut it here. And then we're also going to look at this red circle and the blue circle. Well, the red circle is going to be cutting it along this surface, right? Cutting it kind of in and out of the page. And then finally, we're going to be cutting our cube this direction, right? Because we effectively have three stress states in order to encapsulate all 6 planes, right? All 6 sides of this cube. Because each cut incorporates 4 sides, right? So our blue one, if we look at our blue cut, if we look at our cut up above, we're going to have sigma long pressure's acting towards the surface, have pressure acting. And finally, for our red cut, if we look at that one, we've got our Hooke stress, and then our pressure acting, right? So those are our 3 stress blocks that we get from our stress cube, cutting it in all of the directions that incorporate all of the surfaces of our cube. We essentially will get 3 circles from that, as we did in our stress transformations, right? We live in a 3D world, so we have to look at 3D elements sometimes. And the maximum stress state, or absolute maximum shear stress, right, is the maximum of our outer points that we plot on our Mohr circle, right, which in this case is our red cube. We end up with, this shirt always does that. Tau max absolute equals 1/2, right? It's essentially the radius which equals 1/2 PR over T, we know is our Hooke stress, minus a negative. Our pressure is acting towards the surface, so it's compressive. That's why it's on the left-hand side of our y-axis, right? It's negative. Mohr circle, normal stress is on our x-axis. Positive on the right-hand side of our y-axis means in tension. Left side is in compression. If we go the rest of the way, we get PR over 2T plus P over 2. Well, that's exactly what we got here. right? We'll look at an example, but if we had a propane tank, right, we're going to have some material specified for that propane tank. That material is going to have an allowable shear stress and allowable normal stress. We would use our Hooke and longitudinal stresses to verify our normal stresses are adequate, right, if we added in a factor of safety potentially. And then we also have allowable shear stress. We would want to relate that back to our maximum absolute value of our shear stress in our section, which would mean we would use this equation here. And this equation here is based on these three stress states, right? Plane stress states. Right, we have in plane and out of plane Mohr circles. We do the exact same thing for the outer surface. Right, we have our stress cube, and we're now going to cut this cube in 3 directions in order to encapsulate all effective combinations of our radial stress, our Hooke stress, and our longitudinal stress. Essentially exactly what we just did here. And we're going to do that, and we're going to figure out that our tau max absolute value equals our Hooke stress. As you can see, it's our far right one minus our radial stress again. Equals 1/2 PR over T minus 0 now, right? The pressure on the outer surface is 0. So we get PR over 2T. As you can see, the inner surface sees a little bit more shear stress than our outer surface, right? Because it has that additional force of additional stress of the air pressure or fluid pressure or whatever was in it in this tank acting on the stress cube. Again, I'm going to just give this to you. At the outer surface, if we look at chapter 13, utilizing Hooke's law, we can get the strain in the longitudinal direction and the strain in the Hooke direction. And that ends up being 1 over the modulus of elasticity times the longitudinal stress minus Poisson's ratio times the Hooke stress, which if you plug in all the values that we just derived, right, where this is Poisson's ratio, and in the Hooke direction, we're going to have different strain, right? We have different stress. Our Hooke stress is twice. So we're going to get 1 over E, our Hooke stress, minus Poisson's ratio times our longitudinal stress. Plug everything in. We got the pressure times your inside radius times 2T times modulus of elasticity times 2 minus Poisson's ratio. Right, and if you knew the strain around the perimeter of a propane tank, as you increase the pressure, right? So you increase the pressure and change some of the geometry, the inside radius, the thickness, maybe change the material, change the modulus of elasticity. You can calculate how much that tank is going to deform, right? How much larger is it going to get? And sometimes that can be a design constraint as well, right? We don't want something to go too far with respect to deformation. Don't want it to enlarge itself. Might be a pressure vessel that slides inside of something. So we would want to verify that it doesn't increase by too much, right? This strain is in the circumference of our propane tank. So knowing that strain is change in length over the original length, we knew what strain was and we knew what the original length was, we could figure out what the change in length was. We could add that to the original length and we could figure out how much bigger the circumference got. If we know how much bigger the circumference got, we can figure out how much bigger the radius it gets. Right? You guys seem just as excited about this as I am wind loads. That's your? Wind loads. Maybe. Ecstatic. Pumped. So, all right, let's do a real world example here, okay? Anybody scuba dive? Sick. Sick. Advanced, or are you certified? Advanced open water, or are you more than that? Advanced?
Since I moved here, I haven't gotten any more serious.
Okay. I'm advanced and I go like once every year-ish, 2 years-ish. So I usually have to do like a refresher every time.
I need a refresher.
Yeah, seriously. There's a lot going on, especially when you're like 100 feet down and you freak out about something. It's always great. But they're like, in the thing, they make you take your goggles off and your regulator out. And they have to clear everything and you're at the bottom of the ocean. I recommend it. I do. It's a lot of fun. But a real world problem that relates to scuba diving, well, we have a cylindrical tank on our back as scuba divers. Okay? And that cylindrical tank is, well, in this case, we got a 7.2 inch diameter tank with a wall thickness of almost a little over ½ an inch. Okay? And the air pressure in the tank is over 3,000 psi, so 3,500 psi. It's very, very real world. They're close to it. Okay? And they want us to figure out what is the longitudinal and Hooke stresses in the wall of the tank. And also we want to know what's the maximum shear stress in the plane of the cylinder wall. Right? Maximum shear stress in the plane of the cylinder wall. Well, if we're looking at in plane versus out of plane, right? In plane Mohr's circle, that's looking at our green stress cube, right? In plane meaning that we're looking at the stresses that are in the plane of our tank. Well, that would be our Hooke stress and our longitudinal stress, right? So they really want to know what's going on with this circle. What's the shear stress in plane? And then they come and ask us, what's the absolute maximum shear stress on the outer surface of the cylinder wall? Okay. Well, let's talk about what we know. Well, it says the outside diameter of the tank is 7.2 inches. Well, we don't give a shit about the outside diameter. We care about the inside diameter, right? As I mentioned before, it's always R sub I or D sub I. Don't worry about the outside. So we need to figure out what the inside is. Well, we were given that D naught, or DO sub O, 7.2 inches. And we were also given the thickness is 0.55 inches. Well, our inside diameter is just the outside diameter minus 2 times the thickness. That's 6.1 inches, I hope. Well, we always want to double check that we're dealing with thin-walled vessels. Our stress assumptions, we're assuming that our stress is relatively uniform. We don't have all these crazy peaks and valleys of stresses due to thick wall behavior. So we want to verify that. Well, our diameter over thickness is 6.1 over 0.55. That's 11. Why did I do that? Right? It's like, what? Yeah, but it's also the radius, not the diameter. Which would also make this not work. Yes, this is a thick walled tank. Okay? It's just like it dawned on me just now, so anyway. But then I'd have to redo all the calculations, and I don't like to run numbers. Okay? So I'm here talking to all of you. I give you homework, and you run the numbers for me. Okay? It's 11. Well, is that greater than 10? Yes. We're going to assume that this is a thin-walled tank. It should be greater than 20 in our case, right? We're just going to do this. We're going to say thick-walled major bummer assume thin. See? Which makes sense, I guess. Half an inch in diameter, so essentially you're taking up an inch. I mean, these tanks are very heavy. But we're going to assume this is thin-walled, so we can continue on, okay? But as mentioned, this is a check that should be conducted, right? To make sure that we can still use our thin-walled approach. And don't use a thin-walled approach if it's a thick-walled tank, okay? Don't say, Tim said I could do this. All right, don't kill anybody. Well, they asked for our longitudinal and Hooke stresses. Well, that's easy. We figured that out already. All right, we have a equation for that based on our derivation. We have the pressure times the inside diameter over 4 times the thickness. So we have 3,500 PSI times 6.1 inches. That's our inside diameter divided by 4 times the thickness. We know is 0.55. We get 9,700 PSI. Our Hooke stresses, well, we know they're just twice PD over 2T. But if we ran the number, 3,500 over 2 times 0.55, we get 2 times 9,700, or approximately 19,400 PSI. That's a lot of stress, right? 19,000 pounds per square inch. Okay. Part B, what's that maximum in-plane shear stress in the cylinder wall? Well, our in-plane stress, we want to look at our in-plane stress block. Our in-plane stress block, we assume some coordinates here, X and Y. We're going to have shear stress. We're going to have sigma Y's, sigma X's, right? And our sigma X, in our case, I'm going to assume is our longitudinal stress. So if we were looking at this cylinder, right, that's our longitudinal stress direction. We've got our sigma hoop direction, right? So we're essentially looking at in plane or in the surface of our cylinder. So that's our stress block. So if sigma X, we're going to assume is sigma longitudinal, which is 9,700 PSI. Sigma Y, we're going to assume now is sigma hoop, twice that, or 19,400 PSI. Tau XY, or tau YX, as we know. Well, we know that's 0, right? There's no shear stress in this stress block oriented along the surface of our cylinder, okay? So if we go, as we have in the past, we draw ourselves a Mohr circle, right? We have stress on our axes. We have normal stress on the x-axis, shear stress on the y-axis, arrows that go like this, counterclockwise is above the x-axis. Well, we're going to have 2 points to plot, right? Essentially have our 2 points on our faces of our stress block that we just determined. We know that our sigma x is 9,700. Our sigma y is 19,400. We have zero shear stress, so our 2 points are going to land on the x-axis. Following? So we're going to have the coordinates for this guy are 9,700, 0. Right? It's a tensile stress. We know it's acting outward. We have 0 shear stress. So we have 9,700, 0. Here we're going to have our sigma y, or our hoop stress, or 19,400, 0. essentially plotting these 2 points, right? Hooke stress and longitudinal stress. And the circle that we're going to create is what we would call our in-plane Mohr circle. We go here and I'm going to make a beautiful circle. Nope. Now I'm going to make a beautiful circle. Something like that. On our maximum in-plane shear stress is this point up here, right? Which, based on looking at the inner surface and the outer surface, or no. Yeah, we're worrying about the in-plane. Okay, so we're working about the in-plane. So we have a center with a radius. We're really looking at the radius, right? A radius is going to be our shear stress. Well, our radius, or tau max, equals sigma P1 minus sigma P2 over 2, right? These are our principal stresses. Remember, the definition of principal stress is normal stress without shear stress, points with essentially the points of the Mohr circle on our x-axis. So in this case, our 2 points that we plotted are in-plane stresses, our principal stresses. The maximum magnitude is our first principal stress. Minimum magnitude is our second principal stress. So if we take our maximum stress minus our minimum stress, we divide that by 2, well, that gives us our radius, right? So we've got 19,400 minus 9,700 divided by 2. We end up with 4850 psi. So that's our shear stress, our maximum in-plane shear stress in the cylinder of our tank. Part C asked us to look for the maximum absolute. Now we've got to look at all 3 circles. So if we draw a Mohr circle again, right? And our 3 points on our circle, they ask for the outer surface. We're going to look at our outer surface here, right? We have our Hooke stress, which is going to be the maximum. Our longitudinal stress is going to be half that. And at the outer surface, our radial stress is always 0, right? So we essentially take the Mohr circle that we constructed before, and we're going to add another point to it. And that point is going to be our radial stress, right here. We're going to have a circle that connects 2 and 3. We're going to call this principal stress 3. 2 and 1, and then 1 and 3. And it's the largest circle. That's our maximum or absolute maximum shear stress. So we're going to have 0, 9,500. So we have 19,400, 0. We have 9,700, 0, and we have 0, 0, right? Because we're on the outer surface, our radial stress is 0, right? This is our 3D stress cube. Radial stress is 0. And we have our Hooke stress and our longitudinal stress. We have to make a mixture of all 3 of those. We do that by making 3 stress states. Each of these stress states are 2 points on Mohr circle. So we're going to develop a Mohr circle that looks like this. In our case, we have values for Hooke stress, 19,400. we have our longitudinal stress at 9,700, and then our radial stress because we're on the outside surface of 0. Now we can just draw pretty circles here. Circle 1, circle 2, getting too crazy with this. Oh, shit. Something like that. Right, and this is tau max absolute. Right. Tau max absolute is the radius of a circle. In this case, 9,700 lands right in the middle. So we have this radius of a circle that goes from the origin, or 0, 0, or what we call sigma 3. Right, sigma 3, sigma 2, sigma 1. From sigma 3 to sigma 1. So we got sigma 1 equals our Hooke stress. Sigma 2 is our longitudinal stress. And sigma 3 is our radial stress, which equals 0. So our maximum absolute, essentially saying overall maximum shear stress, is our sigma 1 minus sigma 3 over 2, right? It's just the radius, which is sigma Hooke minus sigma radial over 2, which is 19,400 minus 0 over 2, which means tau max absolute equals 9,704 psi. What's that? Fuck, I don't know. Oh, because in this thing I simplified. We'll get rid of that. All right, calm down. Jeez. You're just supposed to blindly just accept what I give you, okay? Don't push back. What are you guys trying to do here? I had this is actually 19,410. Okay, I got rid of the 10, which 4 still makes no sense. So I don't know, all right? Told you I didn't make it out in the real world, that's why I'm here. Yes, I want you to go in the real world. I made it just fine out there. Okay, so those are our answers, right? And the reason why we look at those and why we might look at, say, our in-plane maximum shear stress versus our absolute maximum shear stress, okay? The absolute maximum shear stress, well, that has to do with three-dimensionally moving our cube. So there's potentially a surface in this aluminum or whatever material this cylinder is made out of, okay? There's a shear stress in it acting in some direction, right? That's going to be our absolute maximum. For in-plane, though, sometimes, right, when we're building these things, we have joints and connections that we need to make, right? We're going to make something large out of a bunch of smaller things. So in order to do that, we might have a connection, right, a weld of sorts. In this case, it'd be like a spiral weld. If you ever go to a town pump or something, and they have those big propane tanks, and you look at them, right? They've got joints between these steel plates that they use to make these tanks, okay? Those joints might be along the the length of our tank. They might be spiraled. A lot of larger pipe diameters are made out of spiraled plate, okay? So in order to do that, we would need to know what are the stress states that are going on at, say, 30 degrees, which we've already done, right? There's going to be some sort of shear stress and normal stress. stresses that are acting along the length or perpendicular to the length of our weld connection. And we could look at that, right? Based on Mohr Circle. So could look at stress at angles based on Mohr's circle to evaluate materials. Right? That would be our next step in this, is that knowing the geometry and the applied forces being the pressure that we're putting in this scuba tank, we can figure out how those stresses relate to allowable stresses in the material, okay? Any questions on pressure vessels? Nothing? Okay. Well, on Friday, we will start talking about combined loading. It's going to be the last section of this class, okay? We're going to start pulling everything together, right? Axial loads, torsional loads, bending loads, pressure loads, right? Essentially taking everything we've got, put it all together, figure out what stress states and stresses we have in materials. Don't forget the homework, and don't forget the quiz. All right, there's over 30% of your grade still sitting out there right now. Isn't it? Oh, fine. Okay, sounds good. I'm sorry. We're going to make it happen. I will check right now. When we get that. See you later.
I will not be doing it until.
I think we're in here.
I was literally like, no time. Well, no, I don't think it's ever gotten many times.
Yeah, okay. Yeah, I'll check 2 o'clock or 2 and see what's up. Does that sound good?
Click.
See a cool video? Let me